Hello, everyone. Welcome to our presentation on color vector variable fonts. My name is Cosimo Lupo. I'm an engineer in Google Fonts team.
And my name is Dominik Rötsches. I'm an engineer on the Chrome team working on fonts and text rendering.
And my name is Rod Cheater. I'm the tech lead manager for Google Fonts. So I want to start things off by talking a little bit about the current state with regard to color fonts, because I think that'll really set the stage well for the rest of the presentation. So color fonts is not necessarily the font format's proudest moment. Effectively, everybody invented their own format. And with the possible exception of SVG, if you look at it, it's hard not to think that everybody went in and solved their own problem and not necessarily everyone else's problems with color fonts. So there's three main classes. If we look at bitmap formats, which Apple and Google both independently decided to specify, they throw away all the other things the font format can do. They forget vector graphics, forget the ability to tune things to fit on a pixel grid. We get good rendering fidelity, but the cost is that the font file is enormous and not really a font file. No variable fonts, nothing. SVG gives us vector graphics and enormous drawing power. The downside is you require an SVG engine, and again, it's a bit awkward to integrate with the rest of the font format. If you want variable fonts, if you want to map to pixel grids precisely, or you want a compact binary format, you're not necessarily happy. So color v0 is the one that I would say is closest to what you want in a font color format. You reuse all of the font format's existing capability to define vector shapes that was built for drawing letters and everything. You stack a bunch of them on top of each other, and then you color in each layer. You get variations, you get the ability to tie things to pixel grids, you get a nice compact binary font format. Problem is that part about only being able to color them solid. The painting capability is very limited. So I want to quickly walk through what color v0, which is the best vector one in my opinion, does, and then we'll see kind of what we want to do to enhance it. So color v0 starts off, you define shapes exactly the way you would with a letter. So at the beginning, when you're first defining the shapes, they don't have color. They're just drawn in whatever the text color is. The extension that color makes to that is that you can stack them up and apply colors. So maybe we'll start off with that glyph, but we'll color it yellow. Then we'll put that glyph on top of it in brown. And let's add another glyph, also in brown. And now we have a smiley. So we can see here that for some types of emoji, this can actually work really well. This is a good rendering of the Twimoji smiley. It's not so good when you get to anything that goes beyond solid colors. So unfortunately, here's the Noto emoji version of the same smiley. It's using gradients. It's very hard to express using the original color format.
So in color v1, we propose to extend color v0. We're adding definitions for linear gradients, radial gradients, and layer transforms and compositing. And we aim to provide a lot of flexibility and expressivity in adding these graphical primitives. Let's go to the next slide. For linear gradients, we allow powerful definitions. We allow control over the rotation and skewing of the gradients, and also fine control over the color stops. So you can have multiple color stops. You can control the repeat modes at the end or at the edges of the gradient, or etc. And for radial gradients as well, we allow and we add flexible and powerful definitions. Our radial gradient definitions is drawn as a gradient between two ellipses. That's sometimes also called a conical gradient. So in the simple case, this can be an inner and an outer circle, as you see in the upper picture, but there's more flexibility. You can add a transformation matrix that allows you to shear or rotate the ellipses. And again, there's control over the repeat mode, the color stops, and the transparency. Rod will continue and explain how it all fits together.
So in the new version of color that we're proposing, you start off exactly the same way as the existing color. you define the basic shapes you want to use. And at this point, they have no defined color. But now we add the ability to paint them, including gradients. So already we've got a nice move. We can define a Noto emoji made up of these shapes, and that works out quite well for us. But while we're here, we should see if we can improve anything else. So instead of having a flat list of solid layers, we'll have a graph of reusable parts with flexible paints. We'll also allow use of other color glyphs as units of reuse. So if you have a common backdrop made up of 3 or 4 layers, you can just say, I want to use that at this point in my graph. And we'll allow the explicit encoding of transformed shapes in our graph. And then instead of just allowing layers to be plastered on top of each other, we'll allow all the standard blend modes. You can clip a layer with another layer, darken, lighten, this type of thing. So I think it'll help to look at an example. So we'll start off with these outlines. They're the same basic outlines we were using for color v0. We're going to define a first set of color glyphs, which are themselves going to be reused. So previously, we would have had to re-encode use outline A and color B in every color glyph that did it. And in some cases, there would be a common stack that would recur across a whole bunch of them. Now we can actually reuse the stack of colored layers as a unit. So the basic Noto emoji, for example, has a common face backdrop that's made up of a couple of painted shapes. There are multiple emoji that use the same eyes, the same smile. So let's look at an example of putting these together to build something. So in this case, we're going to reuse those color glyphs that we originally defined, and we'll put the smile on top of the eyes layer on top of the backdrop, and we've got a basic color emoji. This one's a little more interesting. We're going to reuse the same parts without introducing anything new. But when we define this emoji, we'll say, okay, we're going to take the smile, apply a transform to flip it and maybe shift it around a little bit, and then take the eyes and the backdrop. And this is using a 2x3 affine transform, and that gives us quite a lot of flexibility in moving things around. So similarly, we can do the upside down face. In this case, we're flipping the smile around, moving it, flipping the eyes around and moving them, and then dropping the whole thing over the common backdrop. The nice thing is we haven't had to define any more geometry. We're just defining how the parts fit together. And if you start looking at emoji, you really start to see there are a lot of repeated parts. And the color v1 format is intended to allow a smart compiler to take advantage of that to produce a very compact representation. All of my examples are emoji, but nothing about the way this format is set up is unique to emoji. You just give it shapes, the compiler finds out where you have reusable parts and figures out how to take advantage of it.
So with these graphical tools and concepts defined, we have a very versatile toolbox that allows us to make an emoji font, for example. And we did that as a validation of our spec proposal. We took the imagery that we have for Noto color emoji and the imagery that's available for the Twitter emoji files and produced a prototype emoji font out of it. And let's look at the results of that. If you compare the size of the emoji font, the Noto emoji font made as a bitmap font in the CBDT format, and then WOV2 compress it, which is the widely used compression standard for web fonts, we see that going from the bitmap font to vector shapes in the color v1 format, we arrive at 1/5 of the size of the bitmap font. At the same time, with the vector format, or being a vector format, we can render it sharply at any font size compared to the suboptimal bitmap interpolation result that we would get from drawing from the bitmap when it's drawn at something other than the encoded image size. We also want to talk about concepts that guided the design for the color v1 format. As Rod mentioned previously, previous formats like CBDT and SBIX and SVG in OpenType are existing color font formats that embed external formats. They're not exactly a definition of font concepts, but they're embedding external formats into the font. We wanted to design a progressive enhancement to the open font format. The design is also backwards compatible with color v0, And we wanted to be able to use color fonts that reuse concepts in OpenType that, for example, use the same shape concepts, same outline concepts, and support variations. Another principle that guided our design is a complex preprocessing stage, or a powerful preprocessing stage that shifts complexity from the rasterization to preprocessing. We'll have more details on that in the next slide, or in the upcoming slides. Another idea that guided the design of Color V1 was to take powerful concepts from existing 2D graphics libraries and open them up or unlock them to be used in the font format. Common 2D graphics libraries such as Skia, Cairo, Cortex, and Direct2D all share a set of common concepts that have been widely used in the industry before and that also found their way into W3C standardizations. For example, clip and fill operations, transform operations, and compositing operations, such as the Porter-Duff operators that are named after the original paper by Porter and Duff, but also defined as a W3C compositing standards. So in the spec proposal, we are unlocking these concepts to be used in the font format, and so that we have a pipeline from font to font parsing to using principles and concepts of 2D graphics software libraries. In the next section, we're explaining what public materials we have available and where you can find our spec proposal and what public software we've released and presented so far. First of all, of course, our current spec proposal you can find here on GitHub. The spec proposal was authored by Bedard Esfabot, Roderick Scheiter, and myself, with input from Cosimo Lupo, Benjamin Wagner from the Skia team, Peter Constable, and Dave Crossland, and others who have helped to review the proposal. Spec is developed in public, and we're using GitHub's issue tracking.
So alongside the draft spec proposal, we've also written tools to build the newly proposed color fonts. These projects also are hosted on GitHub and are open source. This toolchain comprises three main components. The first is called Pico SVG and is a tool to simplify SVGs, like convert them into Pico, small SVGs. I will explain what that means later. And then FontTools is a popular Python library for manipulating OpenType fonts, a pre-existing project, but we contributed to it. Specifically for this project, we added an API for programmatically building color V1 tables. And then NanoEmoji uses the previous two components plus other libraries to compile SVG documents as input, as their source, into color fonts of various formats. Next slide, please. So to go more deep in depth, Pico SVG basically has a sort of canonical definition of what an SVG should look like. And it takes advantage of Skia, the graphic library, to basically try to reduce the complexity of SVG and pre-apply at build time a lot of the things that would happen normally when rendering SVGs at runtime. So, like for example, there are no shapes, geometric shapes. There are only path definitions. There are no relative coordinates. The stroked paths are converted into filled outlines. The clipping is applied already to the paths, and the nesting of the groups is is flattened basically as far as is possible, because there are things that we can't ungroup. Next slide. So FontTools, as I said, provides us with an API to create a color table from definitions of the paint, gradient, solid colors, palette, and also a way to inspect the content of the color fonts using the XML format that FontTools uses, called TTX, which is very handy when you're making unit tests, for example, or trying to debug a font. Next slide. And then NanoEmoji is the font compiler, and it also is built on an existing stack of libraries that were developed previously in our font build toolchain called FontMake. So it tries to basically reuse the generic font build pipeline that we already have and translate the color font that we are trying to create into something that we can pass on to the font compiler proper. So we take the SVGs, we simplify them with Pico SVG, and for each of the SVG, we create a color glyph that is composed of several layers. Each one is another glyph that is associated with the paint definition. So the font compiler currently supports the new color CPAL, also the old color CPAL version 0, but most importantly, the new one that we are proposing, and the OpenType SVG format. And there are more color font format coming soon. The bitmap color formats are not supported right now. Next slide. Yes, and also, as well as the software, we also created some experimental builds of two important emoji fonts. One is the Google's Noto color emoji, and the other is Twitter emoji, two emoji, which we use to help develop the rasterization stack and test that our toolchain creates fonts that actually work the way they are intended to work. And also we also use them to make interesting file size comparison in the next slide that show what Dominic was talking about earlier. But I will show them afterwards. First, Dominic.
Yeah, so Cosimo talked about the production pipeline, or the pipeline for producing fonts, and how we have released a set of demo fonts that we worked with in prototyping. And then when you come to the implementation that actually rasterizes and brings those fonts on the screen, we are releasing or preparing open source implementations as additions to the FreeType and Skia open source libraries. So we are augmenting the open source rendering stack with implementations of the format, which means for FreeType, mostly an API that allows you to extract the data structures that are defined in Color V1 and gather the information from the font on how to draw things. And in Skia, we add functionality to take those concepts from the font and connect to the primitives and graphical foundations that Skia provides, and then actually draw them on the screen. So this means in the Skia case that there's a glyph library or a glyph catalog, and then for each Color V1 glyph that you want to draw, Skia reads the layer and graph information from the font and applies clips, fills, transforms, etc. to bring the concepts that are encoded in the font to pixels on the screen. And we mentioned file size gains a few times, and Cosimo will guide us through the findings we had with the prototypes we worked on.
Yes. So, as I said, we don't have currently a way to build a bitmap color fonts. So we took the existing Noto color emoji that was built with a different toolchain as a point of comparison here. So the first row is the CBDT CBLC bitmap color font, which is roughly 9 megabytes. And immediately after, you can see the Color V1 font is less than half the size. It's 4.1 megabytes. Then the OpenType SVG font takes more than 20 megabytes, 21.2. And then OpenType SVG fonts can also be zipped. So if we do that, we shrink it to 5.2 megabytes. Then I want to show after WOF2 compression for web delivery. Next slide. You can see that so the bitmap font doesn't change because it's already fairly compressed in the PNG bitmaps. So it still stays around 8 megabytes, 8.2 megabytes. The color is now 1.5 megabytes, which is an interesting file size. Starts to be something that we may be able to download as a web font, possibly cut in a few pieces. And then the SVG is now smaller than the gzipped version because, of course, compressing one thing twice is not good. But a lot of redundancy now is gone, and the SVG is now 3.1 megabytes. It's still good, but twice the size of the color font. Yeah, we also tried the same with the Twitter emoji in the next slides. Yeah, here you can see next to each other the uncompressed and the WOF2 compressed. You can see how smaller we get after WOF2. Yeah, Emoji is similar, very similar. Next slide. So we have 1.2 megabyte for the color V1, 4.7 for the SVG, and 1.4 for the zipped SVG. And after WOF2, in the next slide, we are now at 0.5, like half megabyte for the color V1, 0.8 megabyte for the SVG, and yeah, I don't even mention the zipped SVG. So basically, next slide. The conclusion is that whether compressed or not, the color V1 is smaller than either the bitmap or the text kind of vector as in SVG. And after WOF2 compression becomes very exciting. So we are pleased with the result. Next slide.
So you saw our results here. You saw the concepts of the proposal, and you saw some of the prototyping we have done and the basic building blocks. So what we can say, Color V1 is our proposal to add widely supported graphical primitives to the open font format, consistent with existing glyph shape vector definitions and consistent with OpenType variations. We have validated our spec proposal so far, and our experiments demonstrate the format's expressivity. They show file size wins and high rendering quality at any font size. The work you've seen here, the spec, the tools, the demos, and the pipeline, and the contributions to the rendering libraries are all available as open source. You can review them, you can make your own contributions, you can send us feedback. It's all available online in the links that we've shown. Cosimo will talk more about the next steps.
Yes. So, of course, the very next step is land the Color V1 proposal in the OpenType, open font format spec. And we'll do that through making a second review of the proposal with all the stakeholders. Hopefully, we are on a good path. And then after we do that, we will like to try tackle another problem that has to do with the limitation currently in the font format to only allow up to 65,000 and something glyphs in each font file. And we would like to extend that to practically infinite by changing the glyph indexes from 16-bit to 32-bit unsigned integers. So this would allow us to solve an issue relating to color fonts specifically, which since we are using a glyph slot for each of the layers, and we can potentially exhaust the available pool of glyphs in a given font file. So hopefully by raising 32-bit, we can work around that. And it would solve also other issues like CJK or Pan Unicode fonts, but we'll see. Then another thing we would like to do after is allow to interpolate colors at runtime, the same way we do with outlines for variable fonts. But this is not trivial. I mean, it is already solved problem. We just have to put it in spec. We will have to convert between like different color spaces to allow linear interpolation of colors. Then finally, there were some discussions on supporting advanced gradients like mesh gradients, like Illustrator or SVG2 has. But we will see later, because we wanted to do it immediately, but then we decided to push it to future refinement of the spec, because otherwise there would be too much pork in the bill, as they say. And with that, I think we concluded our presentation. I don't know if you want to say something, Rod or Dominic.
Yeah, this is our presentation. We're happy if you take a look at the materials we're providing, and hope you enjoyed our presentation.